Getting the temperature in a building to feel just right, well, it's not luck. It's actually a pretty precise science called HVAC load calculation. And today we're going to break down how engineers go from pure guesswork to pinpoint precision, making sure any space you're in is perfectly comfortable.
You know the feeling, right? You're fighting over the thermostat, maybe wearing a sweater in the middle of summer. Almost every single time, that's a sign of one core problem. The HVAC system was sized all wrong. And look, getting it wrong isn't just about being uncomfortable. It means wasted energy, crazy high bills, and it can even shorten the life of the equipment. But getting it right? That's where the magic, and a little bit of math, really comes in.
So let's dive in and really get into the science of sizing your comfort.
So what even is an HVAC load calculation? The best way to think about it is like you're balancing a building's heat budget. You've got heat constantly coming in from all over: the sun, the lights, computers, even our own bodies. A load calculation is just the process of adding all of that up to figure out exactly how much heat you need to pull out of the room to keep things comfortable.
Now, while a full-blown engineering analysis is always going to be the gold standard, sometimes you just need a quick ballpark estimate to get the conversation started. And for that, professionals have some really reliable rules of thumb.
The two main ways to do it quickly really just depend on your preferred unit of measurement. Internationally, you're going to see watts per square meter. Here in the US, it's all about BTUs per square foot. Now, a BTU, that's a British thermal unit, is just a way to measure heat. The easiest way to picture it, think of 1 BTU as the heat from a single lit match. So really, both of these methods are just different ways of counting those matches.
And this table here lays it out perfectly. You just take your building's area and multiply it by a standard number based on what the building is used for. And you can see how the cooling demand just skyrockets as you go from a regular house to a commercial office and then way up for a hospital, which is just packed with people and heat-generating equipment. But you know, for a really important project, a quick estimate just isn't going to cut it. You need precision. And that's when we turn to the gold standard, the ASHRAE method. It's a method that breaks down heat into its two fundamental types.
First up, we've got something called the sensible load. This one's easy. It's literally the heat you can sense or feel. When the sun is beating through a window and you feel your desk getting warm, that's sensible heat. It's the energy that a regular thermometer is actually measuring.
Now, this formula might look a little intense, but the idea behind it is super simple. It's just calculating the heat based on how much air is being moved, that's CFM, or cubic feet per minute, and the temperature difference between inside and outside. That's it.
Okay, now for the secret ingredient. This is the part the simple methods often miss: the latent load. This is the hidden heat. It's the energy that's tied up in the moisture, the humidity in the air. It doesn't actually change the thermometer's temperature, but it's what makes a room feel all sticky and muggy. And getting rid of this moisture is a huge part of what makes an AC system so effective.
And the formula for latent load is pretty similar. But instead of looking at temperature, it focuses on the difference in the amount of moisture, or the humidity ratio, between the indoor air and the outdoor air.
So here's the crucial thing. The whole professional ASHRAE process really just boils down to 4 clear steps. First, calculate the sensible heat you can feel. Then, calculate the latent, hidden heat from the humidity. Add them together to get your total load in BTUs. And finally, you convert that number into the standard unit for sizing AC systems, which is called tons of refrigeration. And that's not a metaphor. 1 ton of refrigeration is literally the cooling power it would take to melt 1 ton of ice in 24 hours. So more tons, way more cooling power.
All right, so theory is great and all, but let's see how these methods actually stack up in the real world. We're going to run the numbers for a pretty typical office space and use all 3 of our techniques. Let's see what happens.
So our case study is a 100 square meter commercial office. That's about 1,100 square feet, give or take. The question is, what size air conditioner does it actually need? First up, let's use the international rule of thumb. We'll take our area, multiply it by the standard value for a commercial space, and boom, we get a result of 5.7 tons of refrigeration. Okay, that's a solid starting point. Keep that number in your head, 5.7.
Okay, now let's try it the American way. We'll convert our area to square feet and use that BTU value.
And check that out. We get 5.8 tons of refrigeration. I mean, that's extremely close to our first estimate, which is what you'd hope for. So we're done, right? Well, not quite.
Now for the main event. Let's run the full, detailed ASHRAE calculation, the one that accounts for both the sensible heat and that hidden latent heat. And the result is 6.7 tons of refrigeration. Whoa!
That's a full ton higher than our quick estimates. And this is why precision really, really matters.
Now, looking at this comparison side by side is what's so fascinating. You can see the rules of thumb were good. They got us in the ballpark. But they underestimated the total load because they didn't really account for all the humidity and other specific details that the ASHRAE method captures. And that difference right there, that's the difference between a comfortable office and a kind of sticky one.
So based on our precise calculation of 6.7 TR, we can make our final call. Since you can't go to the store and buy a 6.7-ton AC unit, they come in standard sizes, we would round up and specify a 7-ton unit. That ensures we have more than enough cooling power to handle the true load of that space. So let's just quickly recap the big ideas here. First, those rules of thumb, they're great for a quick check. But for real accuracy, you have to use the ASHRAE method because it accounts for both the sensible heat, the temperature, and the latent heat, that sticky humidity. And getting the size right is absolutely critical. If you undersize it, you're always going to be uncomfortable. But oversizing is just as bad. It wastes a ton of energy and can't properly dehumidify the space. So the right calculation is always the first step to making the right choice.
So the next time you walk into a room and it just feels perfect, you'll know it wasn't an accident. It was the result of a very precise calculation, a careful balancing act between the visible and the invisible forces of heat. And it kind of makes you wonder, doesn't it? What other hidden calculations are shaping the world all around us?